So there's a scientist by the name of Thomas Bruice, and I'm not sure if I'm saying that properly, but his research group, they were responsible for some pretty instrumental and pretty significant and cool research on something known as the proximity model. So the proximity model investigates basically two reactive groups are going to be able to react with one another a lot easier and faster if they're close to one another. And so to distill down what Bruice's group did, they had basically these three different scenarios. Scenario A, B, and C. Okay, and what they were looking at was the rate of anhydride formation from esters and carboxylates to, well, basically show, they were looking for the formation of an anhydride. And so what they did was in scenario A, they had two carboxylic acids which were next to one another. And what they noticed was that their rate, that was kind of their baseline. When these groups were on separate molecules altogether, they had a reaction rate of, let's just call it 1, compared to model B, where these groups are close to one another. However, they do have some flexibility because we've got our carbonyl carbon, our other carbonyl carbon, and then our oxygen and our oxygen of our esters there. These two carbonyl carbons are separated by 2 carbons, okay? Each one of those bonds has some flexibility to it. So in theory, your molecule could pretty easily look like this. OR, that's an R. It could look like this. Here's a carbon, and I'm just going to draw it pretty crudely here. We could conceivably have our molecule completely stretched out and linear looking like that. But it's important to know that those two groups remain on the same molecule, so their chances of being in close proximity to one another, well, they're greater than in scenario A, where two molecules are separate altogether. And they saw a 10 to the 5th reaction rate reaction rate improvement. Then scenario C, well, we've got those two groups, we've got those two carbonyl carbons, they're separated by the same distance, but we've got this other ring associated with it. This other ring that's basically going to make this structure quite a bit more rigid, and our reaction rate goes up even higher. It's 10 to the 8th faster than when we've got our two starting molecules as separate molecules altogether. Okay, so that proximity model is pretty cool because it's sort of saying, like, if you can ensure that these two groups are as close to one another as possible, you're going to see an improved reaction rate. Now, a question is, or a very fair question is, okay, I understand that we have this this lowering of a delta G double dagger, but how on earth does that happen? Excuse me. Well, Linus Pauling, who won one Nobel Prize and was on the verge of basically winning another one, a very brilliant scientist, proposed that enzymes bind transition states best. So enzyme active sites are complementary to the transition state of the reaction. Okay, so enzymes are going to bind the transition state better than the substrate, which might sound a little bit strange, but essentially what it is it's almost like the substrate as we know it is not something that the enzyme is going to have a very high affinity for, but instead that substrate, as it's beginning to transition to your product, it's going to have a high affinity for that. So stronger and additional interactions with the transition state as compared with the ground state lower the activation barrier. So this is largely going to, so our delta G double dagger is going to drop because our enthalpy transition state is going to be most impacted. Now, how to illustrate this is we have this stick right here, and what we need to do is we need to break that stick in two. That stick, without the presence of an enzyme, it's going to have to go to this transition state and then finally break apart. Well, if you imagine that you have that stick, get it like this, and you bend it, and it snaps. So you're effectively the enzyme there. Your delta G double dagger, your uncatalyzed free energy change, is pretty significant compared to with the help of an enzyme. Okay, what we've got is an enzyme here that has a active site that is complementary to the substrate. Okay, so what that means is effectively we've got our stick, which is our substrate, highlighted as S there. It's going to bind that enzyme substrate complex. And what you notice about this is our free energy goes down. Now, why is that? Well, remember, this enzyme is this enzyme active site is completely complementary to the substrate. So it's going to bind it and just hold on to it. That in order for that enzyme to break that, well, the entire enzyme is going to have to be manipulated. And so your free energy change, your activation energy, I'm sorry, after you've bound your enzyme has actually gone up. Now, rather than going from here to here, we have to go from here to here. So we have to go from that ES complex, that very stable and favorable ES complex, all the way up to that ES double dagger. Okay, so when it comes to like preference, do we want an enzyme that has an active site that's completely complementary to a substrate? No, we don't. Not at all. What we really want is something that looks like this. Let me erase all my markings here. Oh, I suppose I can keep that one. We want an enzyme with an active site that's complementary to the transition state. So what that means is that as soon as that enzyme binds to that substrate, effectively, it's already kind of forcing it to kind of contort itself. So our enzyme certainly has the capacity and affinity to bind to our substrate, but as soon as it does, it's basically kind of forcing together the enzyme or closing off that enzyme in order to break our transition state, or sorry, break our substrate into two pieces, giving us our products. And so our delta G double dagger is getting from our substrate up to here. Yes, we do have that initial binding, and we do have an activation energy for that, but it's not as dramatic, and our ES structure is not more stable than the free substrate. So we get to this ES double dagger, and before you know it, well then, your products are produced. So catalytic mechanisms. So that was all kind of the rundown of enzyme substrate interactions and binding and everything like that. Understanding catalytic mechanisms is very important. Enzymes may use one or a combination of the following. We have acid-base catalysis, covalent catalysis, and metal ion catalysis. So acid-base catalysis is pretty simple and straightforward. Just the exchange of protons, give and take protons. Covalent catalysis, you're going to change your reaction path. And metal ion catalysis, you're going to use redox cofactors that are going to alter pKa's of different groups. Now, when it comes to catalyzing a reaction, it's important to know some of the players that are likely involved. So, since we're talking about an enzyme, we're talking about proteins, well, we have cofactors. There can be metal ions, or there could be organic cofactors that participate in a reaction, but we're largely dependent and reliant upon all of our amino acids. Now, when it comes to amino acids in general, acid-base catalysis, it's important to think about, well, which are the residues that are likely to be involved? These are the, what would that be, 8 amino acids that are most likely to be involved in acid-base catalysis. And you could probably rank them in this order. Glutamic acid, aspartic acid are highly likely to be involved, and tyrosine a little bit less likely. Okay, now glutamic acid and aspartic acid, they can exist as a general acid, in which case they are protonated, or they can be proton acceptors. At a physiological pH, chances are that they are going to be proton acceptors, so they are going to exist as a general base. Lysine and arginine, on the other hand, at a physiological pH, they're probably going to be protonated, so they're going to more than likely act as a general acid. So this just shows the different displays that are, different states that our amino acids are going to be found in, and their protonation state. So this is one of the reasons that I really stress the value of amino acid protonation state, because if you understand that, then you understand acid-base catalysis. You understand how different groups are going to react with one another and everything like that. I hope this is helpful. Have a good one.